Welcome to today's lecture, in which I will continue covering periodic properties of the elements. I just want to tell you a funny story. This morning my wife and I were complaining about how old we sometimes feel. Time seems to go by much more quickly than it used to when we were younger. Our 9-year-old daughter overheard us and said, "You're not that old." I said to her, "Thank you, honey." Then she looked at me and said, "I was talking to Mom." Anyway, I wanted to share you an interesting fun fact. That fact is that silicon gas is toxic. Okay, that doesn't sound very fun, but I happen to have learned this by reading the book Digital Fortress by Dan Brown, who is the author of Angels and Demons and the Da Vinci Code. There's this scene in that book where a pile of computers gets lit on fire and it gasifies all of the silicon chips and the heroes running away from them. And anyway, I just remember reading that and thinking, that's interesting. Silicon gas, toxic. Cool. And now, in the spirit of trying to be funny, I'm going to show you a chemistry cat of the day from quickmeme.com. Two men walk into a bar. The first orders some H2O. The second one says, "Sounds good, I'll have some H2O too." The second man died. After this last set of presentations, which will cover sections 4 through 6 of Chapter 7 and ultimately conclude our coverage of Chapter 7, you guys should be able to do the following. First, know what an isoelectronic series is. Second, derive electron configurations of ions. Third, know periodic table trends in ionization energies and use them to sort examples. Fourth, know periodic table trends in electron affinities and use them to sort examples. And fifth, be familiar with some physical and chemical characteristics of metals, nonmetals, and metalloids. And you should note that we will skip sections 7 and 8 of our text. In this video, I'll teach you the first 3 bullet points: isoelectronic series, electron configurations of ions, and knowing periodic trends in ionization energies and using them to sort examples. So, different ions of different elements can have the same number of electrons. For example, the following ions all have the same number of electrons. If you look at the periodic table, you'll notice that all of these have the same electron configuration of neon. So, a series of different ions that all have the same number of electrons is called an isoelectronic series. That takes us then to a problem from the problem sets that I ask my students in class. First, what is an isoelectronic series? Okay, I think I just defined that in the previous slide. And which neutral atom is isoelectronic with each of the following ions? Next, consider the isoelectronic ions fluoride and sodium cation. Which ion is smaller? Now, I encourage you to try and answer these questions on your own first. If you'd like, I'll post a link here to a separate video in which I answer them on the board. I'll now teach you about the electron configurations of ions. Now, just as we can do with neutral atoms, we can derive the electron configurations of ions. For example, if we were asked to give the electron configuration of sodium cation, here's what we do. First, we derive the electron configuration of neutral sodium, which happens to be this thing right here. Second, starting with the outermost orbital, we remove the same number of electrons as have been removed to form the ion. In the case of sodium plus, only one electron has been removed. So we take it away from the 3s orbital, this outermost orbital here. So the new electron configuration is 1s2, 2s2, 2p6, which happens to be the electron configuration of sodium plus. Now, if I had an ion that was a negatively charged ion, I would go in reverse. That is, I would add electrons to the outermost orbitals. You should notice, by the way, that this happens to be the same electron configuration as neon. So sodium plus and neon are isoelectronic. That takes us to a problem. Write the electron configurations for the following ions. I invite you, of course, to do these on your own. And if you like, I'll post a link here to a separate video in which I show you the answers on the board. I'd now like to teach you about ionization energies. As it turns out, it takes energy to remove electrons from an atom, even for atoms that want to give up their electrons. The energy required to remove an atom's electron is called its ionization energy. The first ionization energy is the energy required to remove the first electron from a neutral atom. The second ionization energy is the energy required to remove a second electron from an atom. And the larger the ionization energy, the harder it is to remove an electron. Electrons in higher energy orbitals, by the way, are further from the nucleus, so they're easier to remove. For example, it's easier to remove an electron from a 3s orbital than it is from a 2s orbital, because a 3s orbital electron is further away from the protons in the nucleus that are sucking it in than a 2s orbital. This table shows us various ionization energies for different elements. Sodium, for example, you'd imagine, would want to give up its first electron, because it wants to be isoelectronic with neon. but it still takes energy to remove that first electron. In fact, it takes 496 kilojoules to remove that single electron from a mole of sodium. At that point, sodium now feels like neon. How much energy does it take to remove a second electron from sodium, making it Na2+? Well, you can see that it takes a lot more energy. And I hope that makes sense. Sodium wants to have a +1 charge, but it does not want to have a +2 charge. For magnesium, we can see the amount of energy it takes to remove its first electron and its second electron. At this point, magnesium now also feels like neon. Is magnesium going to want to give up that third electron and feel like magnesium 3+? Absolutely not. So you can therefore see that there's a dramatic increase in the amount of energy required to remove a third electron from magnesium. This trend holds true for each of the elements in row 3 of the periodic table. You'll also notice as we go down a column that the first ionization energy for each of these elements, which is really going across a row on the periodic table, sodium to magnesium to aluminum and so forth, generally goes up. So as I go from sodium to magnesium, it becomes more difficult to remove an electron. There's an exception with aluminum, but then the trend continues going from silicon to phosphorus and so forth. Why in the world would it be harder to remove a first electron from each of those elements going across a row from left to right on the periodic table? The answer is because as you go from left to right, one element to the next across a row on the periodic table, each element has one more proton in its nucleus, which means that it hugs its valence electrons more tightly and more intensely towards itself than its predecessor in the row. This takes us to some questions that I'm not going to answer here, but we'll just ask and let you think about. These are in fact thought questions. Why do you think that the first ionization energy is so small for sodium? Why is the second ionization so much larger for sodium? And referring to the periodic table, arrange the following atoms in order of increasing first ionization energy. This table shows us various ionization energies for most of the elements on the periodic table. These are first ionization energies, that is, the amount of energy required to remove a single electron from each of these respective atoms. That takes us to a series of problem set questions that I give my students in class. First, why does lithium have a larger first ionization energy than sodium? Second, what is the general relationship between the size of an atom and its first ionization energy? And third, which element in the periodic table has the largest ionization energy, and which one has the smallest? Next, based on their positions in the periodic table, predict which atom of the following pairs will have the smallest first ionization energy. Now, I'd like you to attempt to do all of these questions on your own. If you'd like to, I'm going to put a link here to a separate video in which I answer them on the board. That takes us to the end of this video. Please stay tuned to the next one in which I will talk about electron affinities to affinity and beyond. Until then, have an enjoyable rest of your day.